Hey guys, welcome to video 55. Today we're going to take another look at the equations we derived in the last video. We're going to analyze an actual collector feedback biased 2N3904 common emitter amplifier. We'll do some PSpice simulations and we're going to introduce Miller's theorem. Let's start right now by looking at the schematic we have on the screen here. Starting with the input resistance equation, this is the full accuracy version. We're including the load resistor in this calculation, so we're using R prime C in this equation. If we analyze the circuit with no load, if we remove RL, we would just replace R prime C with RC. All right, the output resistance is a fairly complex equation. It does not include RL by definition, because when we're determining output resistance, we're looking into the amplifier from the perspective of RL. And finally, we've got the voltage gain equation down here with what we would consider to be the open loop gain of the amplifier, alpha times negative R prime C over little re, times a correction factor that applies when we include the feedback resistor. Now, what I want to do next is take a quick look at Miller's theorem. Here we see we've got the block diagram symbol for an inverting amplifier, and Miller's theorem says that if we connect a resistor RF from the output to the input of this amplifier, we can split that resistor into two parts: an input part that's scaled by a factor of 1 over 1 plus the gain magnitude, and an output part that's scaled by a factor of gain magnitude over 1 plus the gain magnitude. Now, we've seen this input scaling factor fall out of our derivations previously. In the last video, at about the 7-minute mark, this equation was mentioned. And if you go back to video 46, where we were talking about the enhancement mode MOSFET with drain feedback, we saw this equation drop out at about the 13-minute mark. So if you want to see it where it comes out naturally from our analysis, go back to those videos. We're going to compare these equations with the results that we derived previously, and we'll see that there can be some differences occasionally. Normally it's not very significant, but it's there, and we'll talk about that. Now, before we go on, I also wanted to mention that if you put a capacitor in the feedback loop of an inverting amplifier, it gets scaled as well by the inverse of these relationships for the resistive case. On the input of the amplifier, we see an equivalent capacitance that's 1 plus the gain magnitude times larger than C sub F. And on the output, we see an equivalent capacitance that's 1 plus the gain magnitude over the gain magnitude times larger. So in this case, the capacitor appears larger. In the resistive case, the resistor appears smaller. Now, the significance of the capacitor in the feedback loop is that it can drastically affect the frequency response of the amplifier. And we're going to derive this relationship sometime in a future video, but for right now, I just wanted to mention that. And now let's go on back up and work an actual problem with a transistor. Okay, the circuit we're going to work with is shown here. We've got a 2N3904 with a beta of about 100. That means alpha is about 0.99. V sub phi, the barrier potential, is about 0.7 volts. V sub T, thermal voltage, about 26 millivolts. And the emission coefficient eta is about 1.5, pretty typical for this transistor. We're going to start with a quick DC analysis, and first thing we calculate is ICQ, which is going to be VCC minus VBE divided by RF over beta plus RC. Now, RF is 270K divided by 100 is 2.7K, plus 2K is 4.7K. That'll be our denominator. So let's call up our calculator here. We've got 9.3 volts divided by 4,700 ohms is a collector current of about, let's just call it 2 milliamps. Okay, So ICQ is 2 milliamps. VCEQ is, recall, VCEQ equals VCC minus ICQ times RC. So we've got IC times RC is going to be 2 milliamps times 2K is 4 volts. So we've got 10 volts minus 4 volts equals 6 volts. So our VCEQ is 6 volts. For the DC load line, VCE cutoff is the power supply rail voltage, so that's 10 volts. And IC sat is VCC over RC, so 10 volts divided by 2K is 5 milliamps. All right, now just for the heck of it, let's go on over and plot our DC load line. So we're at 10 volts for VCE cutoff and 5 milliamps for IC sat. So if we draw that line in, here we go. Our Q point is located at 2 milliamps and 6 volts. So here's our Q point. And let's go on now and do our large signal AC analysis. R prime C we found already. That's RC in parallel with RL. That's 1 k ohm. The AC collector saturation current, remember, is IC sat equals ICQ plus VCEQ over R prime C. I know that's a little hard to read, but we've got 2 milliamps plus 6 volts divided by 1 k ohm. So that's 2 milliamps plus 6 milliamps equals 8 milliamps. There is our collector saturation current for the AC load line, 8 milliamps. All right, let's see. I'll do the VCE cutoff down here. VCE cutoff is equal to VCEQ plus ICQ times R prime C. So that gives us 6 volts plus 2 milliamps times 1K is 2 volts. So we get 8 volts. All right, so 8 milliamps and 8 volts. Let's construct our AC load line. We'll use red this time. So we're going 8 milliamps to 8 volts, and there's our AC load line. It goes through the Q point here, and we can see that VO max is going to be VCEQ over R prime C, and that was 2 volts. Let me go back to blue. So we've got 2 volts for our positive clipping point. VO min is negative VCEQ, so that's negative 6 volts. That's our negative clipping point. And there's a quick review of DC and AC load line material. We haven't looked at that for a while, so that's kind of useful here. Okay, let's clear off our desktop here, make a little bit of room so we can do our small signal analysis. And the first thing we're going to start off with is the determination of little re. Remember, little re equals eta VT over ICQ. So eta is 1.5 times 26 millivolts. Let's see what we've got here. 1.5 times 26 mils is 39 divided by ICQ, which is 2 milliamps. So divided by 2 is 19.5. And let's just call that 20 ohms, okay? So little re is about 20 ohms. R sub pi is, remember, beta plus 1 times little re. So 101 times 20 is 2020 ohms. And we'd probably round that to 2000, but let's stay accurate here and call it 2020. All right, now finally, our voltage gain magnitude open loop is equal to alpha times R prime C over little re. R prime C is 1000 ohms divided by 20 is 50 times 0.99. Let me call up the calculator here. And we've got 50 times 0.99. It's, well, 49.5. We could call it 50, but we'll go with 49.5, okay? 49.5. Okay, next on the agenda is for us to determine AV with feedback, the input resistance looking into RF from the input side, and the overall input resistance, and the output resistance, which I haven't listed here, but I do have the equation. Now, I'm not even going to try and enter all these parameters into this terrible Microsoft calculator. It's just atrocious. So I've already calculated those ahead of time, and I'm just going to paste them here. And I'll put those right underneath the formulas. And here we go. Our voltage gain with feedback works out to be negative 49.3, only slightly less in magnitude than the open loop voltage gain. So that's negative 49.3. It's hardly worth working out the difference. Are in looking into the feedback resistor itself from the input source perspective is the first term in this equation, and that would be 5,366 ohms, 5366 ohms. And of course the actual overall input resistance is that resistance in parallel with beta plus 1 times little re, r sub pi, and it works out to be 1.47 k ohms. And our output resistance with feedback, we plug everything into this monstrosity, and we come out with 1.98 k ohms. Okay, so I'll write that here. RO with feedback equals 1.98 k ohms. Okay, now I did build this circuit and make some measurements, and we're going to go look at those in a second, but one thing I want to mention first is if we look at the open loop gain magnitude, it's 49.5, and our gain magnitude with feedback is 49.3. There's hardly any difference between these values, and what that means is we really don't have much in the way of negative feedback going on in this circuit. If we did, our feedback gain would be much lower in magnitude than it is. And what that means from a practical standpoint is that all these parameters we have calculated here are really dependent on our transistor. And we know that these are just going to be approximations. They're not really that accurate. So our actual amplifier parameters are very dependent on the transistor, and they could deviate pretty significantly from these values. But let's go on down and see what the real circuit gave us. All right, so here we have on the left is the circuit, breadboarded, and I was doing a measurement of, I guess, voltage gain here. But here's the scope capture. We've got an input voltage of about 25 millivolts peak to peak. The output is about 2 volts peak to peak, so that gives us a gain of about negative 80. That compares with our calculated gain of negative 49.3, and it's off, but I'm not too surprised. The measured input resistance with the feedback resistor is 1.86 k ohms versus 1.47 k calculated, and the measured output resistance was 1.85 k ohms versus the theoretical value of 1.98 k ohms. So there's some pretty good agreement there. All right, now just as a refresher to show you how I measured the input resistance, we'll go on down to the next slide. And what I did was put a 5 k ohm potentiometer in between my V-in source and the amplifier. I set V-in to 30 millivolts peak to peak and adjusted this pot until V-in applied to the base was half of that, or 15 millivolts peak to peak. Here's a scope trace representing the measurements, and when I removed the pot and measured the resistance from terminal A to B, I got 1.86 k ohms. Likewise, to measure the output resistance, what I did was remove the load resistor and replace it with a 5 k ohm pot. Okay, now before I put the pot in there, I adjusted the output for 4 volts peak to peak. Then I connected the pot and adjusted it until Vout was 2 volts peak to peak. At that point, my pot is set to the same resistance as the output resistance of the amplifier. I pull it out, measure the resistance from A to B, and it worked out to be 1.85 k ohms. Okay, so the takeaway from all of this is that we have derived very accurate equations that describe this circuit, but because there's so little negative feedback, most of the amplifier parameters are determined by the transistor values, which are, very hard to estimate accurately unless we sit down and measure them for the transistor, and we're not going to do that very often. But we do have some powerful general analysis equations for this type of circuit. All right, what I want to do next is go on up and look at our active region model for the circuit under small signal conditions, and this is the pi model we've been using, and down below is the R model of the transistor in this circuit. I plan to simulate this with PSpice next, and I'm going to use the R model because it kind of directly reflects the transistor's behavior. If I use the pi model, then I'm specifying this resistor as beta plus 1 times little re, and that's kind of like cheating a little bit. Down here is just little re, and we let the simulation take care of whether this equivalent resistance is valid or not. Now, to make the simulation a little bit more interesting this time, I'm going to use relatively low values for the resistors in the circuit. We're going to set RC to 100 ohms, RF is 400 ohms, little re is 10 ohms, and we're going to use a relatively low beta of 5. That means that we really can't apply any simplifying approximations to these equations. We're going to use them in their full accuracy to get accurate results this time. In the previous circuit, RF was huge and beta was pretty large, so that would have allowed us to simplify these equations quite a bit and still get accurate answers. This time, that's not really the case. All right, so rather than use the Microsoft calculator to crunch these numbers, that would be way too painful. I did them ahead of time, and I'm just going to paste them in here. And this is what we come up with. Our feedback gain is negative 6.5, the input resistance is 28.3 ohms, and our output resistance is 80.41 ohms. What we're going to do next is bring up PSpice and simulate this circuit and see what kind of agreement we get. Okay, here is our PSpice schematic editor. I've already drawn the circuit to save a little time. In the center, we've got our controlled current source I'm using to model the transistor. I've set the gain of this device to 5. That's the same as the beta for our transistor. And the input source is shown as a sine wave, but this particular source can also provide DC levels. If we look at its parameters, I set all of its voltages, DC and AC, to 1, and I set the frequency to 1 kilohertz. We're not going to be doing an AC or transient analysis, but I have to set that to something to keep PSpice from throwing an error, so I set it to 1 kilohertz. Okay, there's our circuit, and let's just go ahead and simulate it. We don't need that, and we'll turn on our voltage markers, and there we see our input voltage of 1 volt produces an output voltage of negative 6.467 volts, so that's our voltage gain, negative 6.467. All right, let's go ahead and find the input resistance. We're going to do that by dividing V in by the current we're drawing from this source. So we'll turn on our current markers, and we've got an input current of 35.33 milliamps. So our input resistance, according to PSpice, is 1 divided by 0.03533, and that is 28.3 ohms. And let's see what we were predicting. Negative 6.5 for the voltage gain, pretty darn close, but Rn with feedback is right on the money. We predicted 28.3 and PSpice gave us 28.3. So let me write those down before I forget them. We had a voltage gain of negative 6.467 and an input resistance of 28.3 ohms. Next, we're going to determine the output resistance with feedback, and I'll do that by measuring the short circuit output current. So let's bring PSpice back up again. I'll turn off these current markers for now, and let's put a current probe across the output. That's just like an ammeter with 0 ohms resistance. So here we go. We've got an I probe. I'll wire that into the circuit. There we go. Let's, whoops, come on. There we go. Let's get an analog ground for the bottom of it. And, oops, let's re-simulate the circuit. Let me get rid of that. Simulate. Okay, don't need this. And our output current is 80.83 milliamps. All right, so let me get up the calculator here. The output voltage we had was 6. It was negative, but we're just going to go with the magnitude. 6.467 volts divided by 0.08083, and that gives us a resistance of 80 ohms, almost right on the money. And we predicted 80.41. So we're very, very close. Could be a little bit of rounding in PSpice or perhaps in somewhere in my calculations, but we're really, really close. And I think the PSpice results give us a pretty good indication that what we did here in the derivations was all good. Well, it looks like my messy handwriting has magically transformed into nice typeset results. That's because Windows decided to reboot my computer last night, and I lost that handwriting, but that's okay. So we're going to wrap up this video next by comparing the results we've gotten so far with the normal linear circuit analysis techniques, PSpice, and now we're going to apply Miller's theorem and see what it gives us. So here's our circuit with the component values we're using and our gain magnitude, which is alpha times RC over little re, and alpha is beta over beta plus 1, 5/6. And here's the Miller representation we talked about earlier. We're defining the Miller input resistance here, and that would appear in parallel with beta plus 1 times little re, which is reflected in the equation over here for the input resistance. And likewise, RF appears in parallel with RC, and that's reflected in this equation. So when we compare the results, the standard linear circuit analysis techniques that I used to derive the equations gave us 28.3 ohms for input resistance. PSpice agreed 100%, and Miller's theorem says it should be 25 ohms. Take from that what you will. I think it's probably really 28.3, but I'm biased. All right, output resistance, my circuit analysis techniques gave 81.52 ohms. PSpice says 80 ohms, and Miller's theorem says 78.1 ohms. Again, which is the most correct? Well, we'd actually have to build this circuit using an ideal controlled current source, which would be a little bit tough, but we could do it. But these are all close enough that I have confidence in all of these techniques. And that wraps it up for today. I think in the next video, I'm going to explore the limitations of ChatGPT in circuit analysis applications, and I think you're going to find that one pretty interesting. So I'll see you guys next time around.